we're learning different ways to reduce friction. Demonstration we want to do today involves quantum levitation. And Quentin, could you shake those two magnets there? Okay, so that's magnetic repulsion. But in our example today, we're going to use this neodymium track here. And we're going to use yttrium, barium, copper oxide superconductors that are being cooled in this liquid nitrogen. So you can see those disks there. And we want to see if this track will allow them to expel the magnetic field around them. So they're not going to be attracted to the track, but they're actually going to expel the magnetic field so they float over the track. So here you can see that it's not touching. It's floating over the track. Now some people say, well, it kind of looks like the superconductor is a magnet, but if you have two of them, they can move over top of one another without being attracted to one another. And that's kind of a neat demonstration too. So here we can have one going this way, we can have the other one going this way, and they won't touch each other. So you can see that they're not magnetic in and of themselves, but they expel the magnetic field around them. And someday, similar to the maglev train that's in China right now, it would be really neat if we could create a superconductor that wouldn't have to be cooled in liquid nitrogen. Imagine a superconductor that could levitate at room temperature. Maybe someday we'll have cars like that. Now, would you say here, Savannah, is there more friction or less friction if the superconductors don't touch the track?
Less.
Yeah, a lot less friction, right? Now, in this demonstration, you can see the superconductor is actually underneath the track, and it's going around even though gravity is acting against it. Here it comes. I think it's over here. Here it comes. But it's underneath the track. And it'll still float like that until it warms up. But as long as it stays cold, it's able to move, even with gravity acting against it. Quantum levitation, pretty cool.